Sketch the graph of the function f of x equals x squared minus 2 over x squared minus 1 by finding all extreme values, inflection points, interval where the function is increasing or decreasing, concave up or concave down, any intercept, and asymptotes. To find the extreme value and the interval where the function is increasing or decreasing, we would need the first derivative. To find the inflection points or the interval where the function is concave up or concave down, we would need the second derivative. And so we will differentiate f of x twice. At prime of x, we use the quotient rule. First, square the denominator. Take the derivative of the numerator, which is 2x times the denominator, x squared minus 1, minus, keep the numerator, x squared minus 2 times the derivative of the denominator, which is 2x. Distribute, we have 2x cubed minus 2x minus 2x times negative x squared is 2x cubed negative, and then 2x times negative 2 is negative 4x, but with the negative it is a plus 4x. The denominator is still x squared minus 1 squared. 2x cubed minus 2x cubed gone. 4x minus 2x in the numerator is 2x. The denominator is x squared minus 1 squared. To find all critical points, we would have to check where f prime of x is 0 or where it is that f prime is undefined. We factor out the denominator and we see that f prime is undefined when the denominator is 0. And so when x equals 1 and when x equals negative 1, f prime is 0 when the numerator 2x equals 0 or when x equals 0. And so we found three critical points: x equals negative 1, x equals 0, and x equals 1. We will do something to these critical points in a minute, but next we find the second derivative. After we simplify this, the first derivative is f prime of x equals 2x over x squared minus 1, the quantity squared. F double prime is, we squared the denominator. The denominator is now x squared minus 1 squared. So when we squared it, we get x squared minus 1 to the fourth. We take the derivative of the numerator, which is 2 times the denominator, x squared minus 1 squared, minus, we keep the numerator, times the derivative of the denominator, which is 2 times x squared minus 1, we lower the power by 1, and then we multiply the inside function using the chain rule. The derivative of x squared minus 1 is 2x, and then we simplify this. We can distribute it, or we can factor out a factor of 2 and a factor of x squared minus 1. What we have left in the first term is a factor of x squared minus 1, which is now a term only. And since we factored out 2 already, there's still 4 left in the second term, and so this is negative 4x squared. The denominator is x squared minus 1 to the fourth. We then set f double prime equal to 0 and solve for x, meaning we will need to simplify the numerator. The numerator is 2 times x squared minus 1 times x squared minus 4x squared is negative 3x squared minus 1 over x squared minus 1 to the fourth. And we can cancel out a factor of x squared minus 1. So the numerator is now 2 times negative 3x squared minus 1 over x squared minus 1 cubed. And this f double prime is undefined when x equals plus or minus 1, the same as f prime. And it is 0 when the numerator is 0 or negative 3x squared minus 1. But negative 3x squared minus 1 is always negative. And so f double prime has no 0. If we set the numerator equal to 0, we won't be able to solve it, or we would have the square root of a negative number, which is not a real number. We cannot find any zeros for the second derivative, but the cut points for the second derivative are still 1 and -1, where the second derivative is undefined. We now construct the sign chart for the first derivative and the second derivative. The first derivative f prime of x is 2x over x minus 1 times x plus 1, the quantities in the denominator squared. F double prime of x is -2 3x squared plus 1 over x squared minus 1 cubed, where we factor out the negative in the second derivative. For the sign of the first derivative, we would use the critical points at the cut points, -1, 0, and 1. We use a test point in each subinterval to determine the sign of the entire subinterval. For the first interval, we pick x equals -2. Remember that the denominator is always positive except at the cut points. And so we only need to check the sign of the numerator. If we plug in -2, 2 times -2 is -4, so f prime is negative in the first subinterval. For the second interval, we use x equals -0.5. 2 times -0.5 is negative. For the next interval, 0 to 1, we pick 0.5. 2 times 0.5 is positive. And for the last interval, we can pick any test point in there, 100, 2. If we plug in 2 into the first derivative, we get positive. And so the function is decreasing from -infinity to -1. We have to stop at -1 because -1 is not in the domain of the function. It then decreases again from -1 to 0. It increases from 0 to 1, and it increases again from 1 to infinity. We cannot use 0 and 1 because those are not in the domain. For the sign of the second derivative, the cut points are -1 and 1. And again, these are not in the domain. We use any test point in the first subinterval, -2 for example, and we plug this into the second derivative. -2 squared is positive. Positive 4 times 3 is 12 plus 1 times negative, so the numerator is negative. We plug in -2 in the denominator. -2 squared is positive 4 minus 1 is 3. And so the numerator is negative, the denominator is positive, so we end up with a negative in the first subinterval. For the second interval, we pick any test point, 0. 3 times 0 is 0. 0 plus 1 is 1. 1 times -2 is negative. And then in the denominator, 0 minus 1 is negative. Negative cubed is negative. This is a negative over a negative, so it is positive. And then we plug a number between 1 to infinity, 1000. We see that the denominator is positive, but the numerator is negative. And so the function is concave up on the interval -1 to 1. It is concave down from -infinity to -1, and it concave down again from 1 to infinity. It is decreasing from -infinity to -1. It decreases again from -1 to 0, increases from 0 to 1, and increase again from 1 to infinity. We still need to find any intercepts. To find the x-intercept, we would set f of x equal to 0, but we only need to find where the numerator is 0. The numerator is x squared minus 2 for f of x, and we set it equal to 0. This is x equals plus or minus the square root of 2. These are the x-intercept. To find the y-intercept, we evaluate f of 0, which is 0 squared minus 2 over 0 squared minus 1, which is -2 over -1 or 2. And so the y-intercept is x equals 0 and y equals 2. To find any asymptote, we notice that the numerator and the denominator has the same power, and so the horizontal asymptote is y equals 1 because x squared over x squared is 1. The vertical asymptote is x equals 1 and x equals negative 1. This is because there is no factor of x minus 1 and x plus 1 in the numerator. And so we know that these are the vertical asymptote but not wholes. To sketch the graph, we start with the x and the y axis and we label any vertical asymptote. The vertical asymptote occurs at x equals negative 1 and x equals 1. Label them clearly. These are not part of the graph. They are the help lines. They guide us the graph of the function. The horizontal asymptote is also y equals 1. Again, label the asymptote clearly, whether they are x equals or y equals. The vertical asymptote occurs at x equals negative 1 and 1. Horizontal asymptote y equals 1. We also have the x-intercept at the square root of 2 and negative the square root of 2. The square root of 2 is roughly 1.4, and so this is the x-intercept, roughly 1.4 and negative 1.4. These are negative the square root of 2 and the square root of 2. There is a y-intercept as well at x equals 0 and y equals 2. Now, we will learn later on to find the end behaviors of this graph, although that was covered in pre-calculus. But we know that from negative infinity to negative 1, the graph is decreasing and concave down. And since the horizontal asymptote is x equals 1, we want to stay close to the horizontal asymptote and also close to the vertical asymptote. This is decreasing and concave down. From negative 1 to 0, the function is decreasing and concave up. We need to hit the y-intercept, and so we start close to the vertical asymptote, decreasing and concave up. From 0 to 1, the function is increasing and concave up, so it follows the same as on the graph on the left. The vertical asymptote is x equals 1. And from 1 to infinity, the graph is increasing and concave down. We stay close to the vertical asymptote, hit the x-intercept, and close to the horizontal asymptote. This is the sketch of the graph of the function.